Thanks for an overly generous introduction. We talk a bit maybe about SGD tomorrow. So what I'm going to be talking today is super basic. So Matusz really asked me to give this is like a bootcamp. There's nothing here. There's definitely none of my, at least today, results. In fact, I don't think today there's anything from the 20th century even. I mean, this is all like very classic stuff. And just to really give the basics, although I have to say that I am maybe presenting it in a particular way that will represent maybe my view of statistical learning theory. Also, since most of you probably know most of this stuff, I hope it'll be nice for you to see it in an organized way, but I try to also give a bit of go back to origin and see, give a bit of historical perspective on especially the start of machine learning. So just generally the plan, what we're going to be talking about, presenting a particular, what I would consider a classic view of statistical learning theory based on bounding capacity through controlling complexity that will make clear what we mean by that. So we'll start by just a bit talking about what is even machine learning. And what is statistical learning. Today we'll focus only on supervised classification as a sort of looking at statistical learning theory in the context of supervised classification. And we'll already see most of the concepts we want to be talking about, learning based on uniform convergence and non-uniform convergence and based on a complexity measure. And then tomorrow we will extend this beyond supervised classification and talk about real valid and scale sensitive losses and generalized learning and see the same concept. And then what I really want to get with this is questioning whether questioning this complexity measure capacity control approach. And I should say, when I say questioning, I'm leaving this open. I mean, I think it's still kind of, in my perspective, I'll ruin the punchline right away for the end of the talk tomorrow. For my mind, it's still kind of open whether this is really the right approach to things, and we really, even though there are a few cracks, and this is still the main story, or whether we really need to develop work in other directions. We do have other directions. Okay, but let me start, and probably the best place to start is 1956 in Dartmouth. It was considered sort of the start of AI, the workshop in artificial intelligence organized by Marvin Minsky and John McCarthy with the help of other luminaries at the time, like Attention Moore from IBM and Claude Shannon, and Nash was, I don't think he's in this picture, but he was also there. And this was really seen as the beginning of AI, but we're not going to talk about AI here. We're going to talk about machine learning, and I don't want to get into what is the relationship between AI and machine learning too much. I also want to say that when these people in 1956 talked about AI, really they talked about what maybe today would call computer science. I mean, complexity, one of the, where is this? Theory of the size of a calculation, right, was one of the topics in AI. So any of you working on complexity theory, you're actually working on AI from this perspective, right? And so this is very broad, and really what they talked about is, how to use computers in general. At the time also, they talked about neural networks, but the view of neural networks was very different. I mean, neural networks at the time was viewed as one possible model of computation. I mean, this is also how, when we think of feed-forward neural networks, feed-forward networks developed by McCollum and Pitts in the late 30s. This is about the same time, within like a span of 4 or 5 years, of Shannon's master thesis, where he introduced Boolean algebra and using logical gates as a model for computation. Now, maybe this is obvious to us, but this was completely shocking at the time. In Turing's work, we also developed a formal model of computation. Neural networks were developed as a competing formal model of competing model of computation, not just formal, but also maybe even slightly, somewhat biologically plausible. And so when they talked about studying neural networks, studying neural networks as a model of computation, like Minsky, for example, in his I think PhD, actually tried to build a neural network again, in order to build a computer. But by 1956, already got disillusioned about it and said, okay, maybe we should just use digital computers instead. Okay, which I guess that's true. But again, this is just talking about computation in general. they talked about AI, and they want to say they didn't talk about machine learning. I mean, they did talk a lot about what we would consider these days AI, but I want to remind everybody, and again, as I said, everything I'm going to say today, hopefully you all know. I'm just trying to remind you. AI for a long time was really not using machine learning at all, right? So AI is based on encoding expert knowledge in a usable way. Like, so for example, one of the maybe first popular AIs, ELIZA. I'm just curious, how many people here have used ELIZA? You know what ELIZA is? It's a chatbot. How many people have programmed ELIZA? Okay. Oh, some people probably. It used to be more common. This was like a. So this is an early chatbot, and it's based, completely. There's no learning here, right? I mean, there's no next word prediction or anything. It's just based on an expert in writing down rules for a conversation. Okay, maybe slightly more sophisticated, and probably one of the first successful, like actually useful AI systems was. General to predict chemical interactions. Again, no learning, just a whole bunch of rules. Okay, and taking this to an extreme, I think this company is still in business, even though Douglas Leonard, unfortunately, is not with us anymore. Is a commercial effort to start an academic and now a commercial effort to build a system entirely based on expertly programmed rules. And this involves, a whole lot. I mean, this is the tens of millions of hand-programmed rules. Okay? So this is not the machine learning approach. Okay? So I want to emphasize two differences between this approach and what we will talk about, which is statistical learning. So the first is all of this has no probabilities in it. Right? It's very very logic-based and combinatorial. And so one issue is whether to use probabilities or logic. And it's a debate that I think has been going on for now, what is it, 70 years now. But from my perspective, I mean, more important even whether we use probabilities or not is whether we use expert knowledge, whether we program things, or whether we learn from data. In the 1956 AI workshop, there's, as far as I can tell, there's only a single participant that actually discussed the idea of learning. Anybody know who that is? Really? Okay, so the only person that talked about learning was Solomonov, who talked about but inductive inference, which is what we would currently call online. Learning. Again, this is still not probabilistic. He added probabilistic formulation to his model, I think 2 years later in 1960, and this was probably the first kind of formalization of learning, and probably the first kind of work in learning theory. The first person who actually probably implemented a learning system that you probably all know is Frank Rosenblatt, and at the same time, 1956. But he was not at the AI. So Rosenblatt was not part of this AI crowd. So he was not in this 1956 workshop. Right? This was sort of seen separate as a different effort. And what Rosenblatt used the perception algorithm to train a kernel method, basically, so a linear method with a nonlinear map. I think that's very important. He definitely talked a lot about the importance of the nonlinear map, so not much has changed, I guess, from 1956 to 2016 or so. And also, this is one of Rosenblatt's tweets at the time. It's Nazdensuk, the embryo. So he talked. This is in the New York Times. In an interview with him, talked to him embryo of electronic computer that he very shortly expects to be able to walk, talk, see, write, reproduce itself, and have a conscious existence. Okay, so this is also maybe not much change since 1956. This is 1958, and 2 years later. The first use of the first introduction of the word machine learning came about the same time, a tiny bit later in 1959, by Arthur Samuel in the game of checkers. And Samuel's used a machine learning approach for checkers. And this is what Samuel's, the way Samuel's discusses the machine learning approach, which I really like, the way he framed it, is to learn to play a better game of checkers that can be played by any person who wrote the program. So the way I interpret it by maybe morphing it a bit is this program is now not based on an expert. It's not that, unlike the dendrial system we saw before, he took some like world expert checker player and tried to milk all these expert rules for how to play checkers from the expert and program them. But actually, the machine learns on its own to play, not based on expert knowledge. And this is really what I see as the definition of machine learning. Like machine learning to me, as an engineering paradigm of using data and examples instead of expert knowledge in order to build some complex system. And so really you can view this on an axis where on one hand we don't use any data at all. We just rely on our expert knowledge. We don't need any data. And what we want to move is like over to the right here. We're not relying on expert knowledge and instead relying only on data. And this is of course a continuum. And you can think of things like, for example, if I have like just train a few parameters, like maybe I have a parametric model for a face and just it has like a few parameters, like 3-4 parameters or something like that, like the distance between the eyes or how oblong it is or something like that. And I train that. Yeah, I'm training based on data, but it's still I'm using a lot of expert knowledge about how a face looks like, right? Really what we want to do is use very little expert knowledge. And the way I would think about how we use expert knowledge, if the same system can do many different things. Same learning rule can do many different things, same model, right? So if I feed it examples of faces, I'll get a face detector. But if I feed it examples of bicycles, I'll get a bike detector. And if I feed email data from different modalities, I'll get, I can feed it text and I'll get a translation system or question answering system, or can use the same model for many different things. So then I would say really that I have very little expert knowledge programmed into this, and because I can do all these things without specific expert knowledge about them. And this is really what our goal here of machine learning is, to push things as far to the right here as we can, like use minimal expert knowledge and just rely on data. Okay? And the problem is we'll see in about like 2 minutes, is we can't go all the way, right? Because we know that if you don't have any expert knowledge at all, if you don't assume anything, then the no free lunch theorems, which we'll see in about 1 minute and 30 seconds, tell us we can't do anything. And the question is kind of how far to the right here can we push things? Okay, so let's start to be a bit more formal in order to ask this question and answer it. And so as I promised today, we'll just be talking about supervised learning. So supervised learning, I want to build a predictor. I want to find a predictor that maps our input domain X's. You can think of these as images, emails, I don't know, whatever you want, into a label space Y. And I'm not being specific here. It's not important what the label space is, but just think of it as binary, as 0, 1 for your comfort. Yes. No, good, it's good. Yeah.
But when you say no, they call for expert systems, it's not completely true, right? The experts presumably learn
the
data, right? And then you're using some sort of feature map that those experts generate.
No. So expert systems, no. So a true expert system, okay, the expert may be based on the expert's expertise on their observations on data. That's not part of my process, right? The way these expert. No, so using data through the expert, that doesn't count from my perspective. So a pure expert system, and there are many systems really based that way. ELISA, for example, is such an example. There's no training at all. You just write down based on your expertise of how conversations work. You write the rules of conversation. Dendrial, as far as I know, does not have any data or training. Okay, it's just based on writing down chemical knowledge.
No, I understand. I'm just
okay.
saying that we have to be a little bit careful, because where does your expertise come from?
Okay, we will talk about that later. I mean, I'm looking from my perspective. I'm a computer scientist. Okay, if I want to do something, okay, do I take the world expert in something and then base the system based on or write down the expert knowledge? I don't care where they got the knowledge, or do I like have to collect data? So anyway, but let me go on to okay. Where was I? Okay. Supervised learning, right? And we want to find our task. We have some true distribution, a population distribution of over X and Y, like images and their label, or email and whether they're spam or not or whatnot. And we want to find our own task is to find a predictor that's good with respect to this population. So it has a small misclassification rate or generalization error, or expected error, population error, or risk, or whatever you want to call it, with respect to this distribution. Okay. And we are doing that instead of based on knowing this distribution, based on an IID sample drawn from this distribution. Okay? So just 2 comments before we move on. One is terminology. Note that I'm referring to from my perspective, I'm referring to this population error risk as the generalization error. Okay, again, this is just a matter of terminology. You can use your own words. But sometimes people think of generalization error in terms of like some gap or difference or stuff like that. But from my perspective, generalization is just exactly this. It's about doing well on the future. Okay, so I don't really care what you do in the training set. That's not part of generalization. So we'll see. We'll talk about it a bit more. The other comment. And I think Matusz already talked about this morning quite a bit about this word, hopefully. Yeah, we're assuming here that we have samples from the distribution and IID samples. Neither of these assumptions are pretty much ever holds, but they will hold in the lecture today. Okay, and then so can we do this? And is there a rule, is there some learning rule, like a mapping from data to examples that will successfully always be able to learn? And the answer is no. And this is what the no free lunch theorem tells us, that basically no rule just can always work. Right? For any learning rule you give me, I know you train your neural network, you use your fancy kernel machine with your super programmed kernel. It's not going to work in the following sense, that there exists some true distribution, so there exists some reality, some source distribution, on which it is possible to get zero error, in which possible there is a predictor that's perfect, but your rule is not going to find it. In fact, your rule is not going to be much better than chance. Okay, so its error is going to be half minus number of examples over the size of the domain. This is just the edge you can get by memorizing, right? So this is the number of samples you've seen, and you basically cannot do any better than memorization. Okay, and indeed, what I do think of generalization is doing beyond memorization. Okay, okay, so that's bad news. So you can't just expect to be able to work. Instead, in order to be able to learn, you need some inductive bias. Okay, and what do I mean by inductive bias? So there are two ways I think to think about it, and this is going to be something we're returning to. One is that your algorithm cannot just treat all realities the same. It has to be biased towards some realities. Okay, so it has to prefer some realities or others. So it has to basically think that some realities are more reasonable than other realities. Okay? Or another way to think about it is the inductive bias is the assumptions that break away from the no free lunch. Right? So without making any assumptions, I cannot get any generalization guarantees. And so the inductive bias are the assumptions that allow me to get generalization guarantees despite the no free lunch. Okay. Well, okay, so let's be concrete. So the simplest type of inductive bias I can think of is flat inductive bias. And that's just saying that some realities are plausible and other realities are not plausible. In other words, we have a hypothesis class, and importantly, I'm focusing here on just some predictors are plausible and some predictors are not plausible. Right? So I don't know which is the correct predictor, but I know that it's, for example, linear predictor in some specific feature space. So I know that it's a decision tree with at most 17 nodes over some set of possible features. Right? So I have this hypothesis class. Okay? And then what we can do, what can we say? Well, so we hopefully all know the answer. In order to get guarantees here, our workhorse is uniform convergence of the empirical error to the expectation over this class. Okay? So what we can say, we're really interested in this population error or generalization error, but we can't measure it because we don't know the true distribution. We have a sample, we can just measure the empirical error. Okay? As the number of samples increases, the empirical errors converge to the expectation, but we want this convergence to be uniform over all predictors in the class. And just by taking a union bound, we can do this at the cost of this low cardinality. I'm assuming you've all seen this uniform convergence guarantee before, union bound. And once we have that, we can say that at least if we're restricting inside the class, the empirical error is a pretty good estimate for the expected error. And so if you want to minimize the expected error, we just minimize the empirical error. And this leads to the empirical risk minimization learning rule. And so find the predictor is most empirical error in our class. Okay, okay. So what is this? Now, let's ask a fun question. What is this generalization bound good for? Like, why do I need even this? What's the point of proving this generalization bound, doing all this, like, Hofding, using Hofding, and then using uniform convergence, and not uniform, because using a union bound? What's the point of all that? So one possible answer is that what this gives us is after I did the training, okay, so I trained my predictor, and now I want to give it to my boss and tell my boss, look, I found a good predictor and it'll work very well. Okay, so this guarantee allows me to do that in a kind of magical way. So I'm not assuming anything about the reality, and I go to my boss and say, look, without making any assumptions about reality, I can promise you that my predictor, I can bound from above the error of my predictor, and from below, but maybe that's not interesting, by things that I can completely calculate. The empirical error they can calculate, and this like deviation term, which just depends on the low cardinality of the class I used, and I know what class I used in order to training, I can completely calculate the right-hand side here. It's an empirical quantity. Okay, and so I can get this like almost unconditional. Okay, I'm assuming I have IID data from the source, but like without any assumption of reality, I can get a guarantee about how good my predictor is, which is kind of magical, but it's also kind of useless. I mean, if this is really what the way you're going to convince your boss that your predictor is good, then you probably should get fired, because a much better way of doing this, right, is to just collect. Doesn't matter really how you train or how big it's discussed. Just get an independent validation set and measure your error on that validation set. Okay, and then you get a much tighter guarantee that doesn't involve at all the complexity of your model class. And you can do this also numerically much better. And in our specific case here, since we're only interested in misclassification loss, this is dead trivial. I think Ryan will talk about how to get such a kind of essentially validation guarantees in more sophisticated settings later. But in our case, this is like just super easy and not worth even thinking about too much. Okay? So why do we bother getting this generalization, getting these concentration guarantees? So from my perspective, much more important in this post-hoc guarantee, which with a calculatable right-hand side, an empirical right-hand side, is just moving things around, and by saying that by using the fact that empirical error is bounded by the empirical error and expectation are close, they can say that minimizing them is similar, and get this a priori guarantee that tells me that if I use my empirical risk minimization procedure, if I minimize the empirical error, I'm also doing a pretty good job at minimizing the generalization error. So in the sense that the generalization error of my ERM is close to the best possible in the class, plus some deviation that goes to zero as my number of samples increases. Okay? So note that this guarantee, I cannot actually calculate it, right? Because I don't actually know what the best possible in the class is. Okay? But it tells me something, it really tells me something about this goal of learning. It tells me that if Julian, who's has a lot of expert knowledge and knows exactly the reality, okay, is going to choose a predictor from my class, like some really good predictor, and I'm just going to use, instead of this expert knowledge, instead of this expert approach without data, he doesn't need data because he knows everything, and I'm just going to, sorry, you're sitting in the hot spot here in the front center, and I'm just going to use data. I'm going to do almost as good as Riyad. How much almost as good? Well, it depends on my expert knowledge and on the and on the number of samples, or maybe a different way, maybe a better way to say it is that the number of samples I needed, the amount of data I need in order to compute with Riyad, depends on scales linearly with the low cardinality of this hypothesis class. And now we can go back to this plot we had before and be a bit more quantitative about it, right? When we said that we're going from like no data to more data, right? So the no data we get, and this maybe goes back a bit to Misha, if our expert knowledge is so exact that we just know exactly what the predictor is, like which predictor won, our hypothesis class is essentially of size 1, low cardinality is 0, and we need 0 data. Okay? If we go all the way over here, where everything is possible, right? So our hypothesis class is size 2 to the size of the domain. Log of that, we need as many points as the points in the domain. We can't do anything but memorize. And anywhere in between, we know exactly how much data we need. It depends on the low cardinality of the size of our model class, or how specific our expert knowledge is. Okay? And another way to see this, you can also think of it in terms of the error decomposition, approximation error, and estimation error. How well does your model class capture reality, and how big it is determines how close you will be to the best in the model class, and that's your estimation error. And this gives us a guideline then for kind of what's the goal of machine learning, right? The whole goal of machine learning, in some sense, is to find model classes that, on one hand, actually capture reality pretty well, like have a small approximation error. On the other hand, are not too big that we can still have small estimation error, that we can still find the best predictor in the class pretty well just based on samples. Okay. Now, and so the question is, can we do that? Do we need a lot of expert knowledge for that? But now what I claim is that actually that's very easy to do. And we have such model classes that capture reality pretty much as well as we want and are, very controlled size. Okay, and this model class is the class of short programs. So if I take, for example, the class of Python programs with at most, like, I don't know, 100 lines of code or something like that, the size of this model class only scales. So the size of the class is exponential in the length of the program, but the low cardinality is just linear in the length of the program. So with an extremely generous calculation, if you allow 7-bit characters and 80 characters per line, then with a 100-line Python program, you end up with a low cardinality of something like 60,000, less than 60,000. So that means that you can, based on data, you can learn a predictor that's as good as the best predictor you can write with 100 lines of ultra compressed and completely unreadable Python code, okay, using only an amount of data which is maybe a few 100,000, right? So it's like 1 over epsilon squared times 60,000, which is nothing. Like, what's a few 100,000 or a few million, even, like training points? It's really, really nothing. And the model class I'm competing with here is super powerful. In fact, going back to my thinking of machine learning as an engineering paradigm, this is really the most powerful way that I want, right? Because what's the point of machine learning? We said the point of machine learning is to use data, for example, instead of expert knowledge. So let's go back to Julian, who's sitting in the front center here. And Julian is not only knows everything, but he's also a very good programmer. Okay, both of these statements are true. And so what I really want to do is replace all this hard work that Julian does based on all his expert knowledge and all his hard programming, and do just as well with data. But what is Julian going to output? Julian is going to write a program, right? I mean, that's, at the end of the day, we want to build computer systems. Okay, so if there's just no program that actually solves the task, then the whole enterprise is, like, pointless anyway, right? It's not like it's not that I am replacing expert knowledge with data. I mean, there's no expert knowledge even, it's not going to help you. So the entire model class, yes, yeah, yeah.
So with these 56,000 examples, you're going to build something that is good as a program, or it's going to be a program?
Excuse me.
I'm not going to. Okay, that's a good question. So what Shafi asked is whether with these, right now I'm not like, okay, what Shafi asked is whether with these 56,000, or it's a bit more because I have to multiply with a few 100,000 examples, I will actually build a program, or I'll just build a function that's as good as a program. Okay, so using empirical risk minimization, I was trying to avoid getting into that, but empirical risk minimization is a proper learning approach. So I will, in fact, the output of empirical risk minimization will be a program, because I'm only optimizing over programs. The word build I'm trying to avoid here, because, let's get to that in a second. But yeah, but I will, the learning rule will output a program. Okay? What?
In my mind, 100-line.
100-line program. Okay, that's going to be as good. It might not be the same as Rian's, but it's going to be as good as, almost as good as Rian's, right? And 100 lines of code. Okay, so this is like completely the ultimate. So from, if we were, so in some sense, we could stop, not just, we can stop this talk now, and we can stop thinking about machine learning at all. This is a completely ultimate machine learning method. In fact, I'm completely certain that searching over small programs is gonna, is better than any machine learning method that anybody uses. Okay, so if it's so good, why don't we use it? And the problem, which is, I suspect, what was maybe bothering Shafi, is that we can't actually, this is why I was avoiding the word build, we can't actually do it, right? I mean, this is like not even computable. So, forget about how long it'll take us, we just can't do it. And even if we avoid computability issues by focusing on maybe time-bounded programs, or more, even much simpler types of predictors, like decision trees or whatever you want, then the real problem here is the computational problem of the search. The sample complexity goes only with log cardinality, so that's great. And that log is really the whole power of machine learning, is that log, right? I need very few examples, but the runtime scales linearly. I have to search over all possibilities, and in some sense, at least naively, and in many cases also provably, scales linearly with the size of the hypothesis class, so would in this case be completely prohibitive. So and I think this is an important thing to emphasize. The reason I'm talking about this so much is because I really think this is an important thing to realize, that machine learning, at least as represented here, statistically, it's just completely trivial. Okay? The whole complication is computational. And this was appreciated also already by Arthur Samuel in 1959, the first paper in machine learning. And what Arthur Samuel writes is, well, there are two approaches to doing this machine learning thing. One is to which he calls the neural net approach, and basically what he describes is basically like training a neural net for data. And again, neural net is just a model of computation, right? Instead of optimizing over programs, I can optimize over Turing machines, I can optimize over neural nets. All these things are equivalent. Okay. And the other, much more efficient approach is to use some, something that uses lots of expert knowledge that was designed to learn certain specific things. Okay? And then he says explicitly the first method would lead to the development of general purpose learning and is the right way to go, but it's a long time before this will be practical because he didn't have GPUs, and so he's taking this second approach. And I think this is again important to realize, but so really the most important thing of machine learning is computation. And despite this, and despite the fact that we are in an institute dedicated to theory of computation, I'm going to completely ignore computation throughout this talk. Okay, so we will not talk about computation, but yeah, keep in mind that that's actually the real elephant in the room here. Okay. So what do I want to talk about more? So until now, we talked about inductive bias that's uniform. So my inductive bias, my prior knowledge is just some things are plausible and some things are not plausible. Okay, but this is oh, sorry, I'm jumping ahead of myself. I need to talk about something else first. Sorry, take that back. Until now, we talked about only cardinality as our complexity measure. Okay? But we frequently want to talk about hypothesis classes that are infinite cardinality. Like, for example, linear predictors, have real valued coefficients. They have infinite cardinality, they're continuous even. And so we can't really think about low cardinality. Can we also bound the bound capacity, get a generalization guarantee, not in terms of cardinality, or another way to think about it is all the classes with the same cardinality, are they equally complex? And of course, we know the answer is no. And the way I want to approach that is through the growth function. So basically what the growth function is for every hypothesis class is a function of a set of points that asks how many possible behaviors can we get in those set of points. So I'm going to have, if I take like 20 different points, I have 2 to the 20, at most 2 to the 20 possible behaviors. How many of these can be realized by my hypothesis class? Okay. And then I look, and so for example, if I have these two hypothesis classes, one is all possible hypothesis class of all possible functions over 100 points, and the other is a hypothesis class which talks about all initial segments over 2 to the 100 points. Both of these classes have the same cardinality. They both have cardinality of 2 to the 100. But if I take a specific set of points, if I take like some 20 points, then in the first case, if I have 20 points, or m points here, then I still have all possible behaviors in those m points, so 2 to the m behaviors. But in the second case, in case of initial segments, if I take m points, I just have m possible initial segments of them, and I only have m or maybe m plus 1. It can take also the empty segment behaviors. Okay, again, I'm going through this extremely quickly. If you haven't seen this before, then I can give you references later. I'm assuming most of you have seen this. And this is really the key here, that I only care about I don't care about how my predictor behaves in points that I haven't seen and will not see. I only care the behaviors on basically just in the training set, or maybe the training set and the test set. Okay, and so I can get my generalization guarantees instead in terms of the log of the total number of functions, just the log of the number of behaviors of this growth function, and this gives us a guarantee in this growth function, but this growth function is like maybe a complicated thing. And the really big magic here comes from a combinatorial result, which tells us that we have a single number that can control this growth function, and that single number is the VC dimension. Okay, good. So I'm just making sure that you all really do know what I'm talking about. Is the VC dimension? Okay, so VC dimension is just the largest number of points I can shatter, or in other words, the largest number of points where all possible behaviors are possible. So the growth function is still 2 to the m. So if we think of my growth function, right? So the red line here is the growth function. It's always bounded by 2 to the m, right? Because there's only on m points, only 2 to the m behaviors. And the VC dimensions is this green line. At what point, what's the largest number of points in which it's still exactly 2 to the m? And why is this so important? Sauer's lemma, or Scherer's lemma, or the VC lemma, or this is developed almost the same time for 3 completely different disciplines, tells us something amazing. It tells us that the single number pretty much tells us exactly how this growth function is going to behave. That if I look at the growth function, it's exponential up to that point, and then polynomial after that, or maybe better to think of it in the terms of the log growth function, because that's really our measure of complexity. So the log growth function grows linearly up to the VC dimension, and then after that, it's basically flat, like it grows at most logarithmically. Okay, oops, I'm supposed to have, I see some, I don't know, whatever, my colors are not good. Okay, and this is quite amazing, right? It tells us that it's not possible that it'll grow and then just go a bit below the blue line. Okay, it'll be linear with a different slope, or it'll be like, I don't know, go like this. It really just becomes almost completely flat after the VC dimension. Okay, and now if we plug this in if we plug this into our generalization bounds in terms of the log covering number, we get our familiar generalization guarantee in terms of the VC dimension. So this really tells us that we can think of the complexity of the class, again, not just in terms of log cardinality, but just in terms of VC dimension. We can handle also infinite classes. We can go beyond that and say, okay, I just told you a few minutes ago that we can control the sample complexity by log cardinality, and now I'm telling you, we can also do it not just log cardinality, by VC dimension. Maybe somebody, I'm going to not pick on Drian so much anymore. Let's move to Matusz. Maybe Matusz will invent a better dimension, the Matusz dimension, which will be even tighter than VC dimension. Okay, is that possible? Like, is it possible that actually there are classes that are learned with much less samples than the VC dimension, or that are learnable even though they have infinite VC dimension? Okay. In order to do that, to get positive results, I just can use theorem to tell you that something is not possible. We have to be a bit more careful, but saying what we mean by learnable, what we mean by sample complexity. And so the notion we'll use is this variance PAC notion, which basically means that we can get guarantees like we did before, right? So that we can get for, and we say positive class is learnable if there exists a learning rule, okay, such that for any epsilon and delta, there's some amount of data that ensures me that I can do as well as Riant with an epsilon for any source distribution. Right? The order of quantifiers is important. I want the sample, what's going on here? I want the sample complexity M to not depend on the source distribution. So this is just for historical completeness. I mean, this is agnostic PAC learning. Valiant's original definition actually was without errors, focused only on the realizable case and limited only to the cases where the approximation error is 0. It's not so important from our perspective here. In fact, what we'll look is not just in this binary notion of learnable and not learnable. What we really care about is how many samples do I need to learn, right? So to find the sample complexity is the smallest number of samples, such that there exists a learning rule that learns to within these number of samples. And again, this depends on epsilon and delta. And now we can ask, does the VC dimension, in fact, always tightly capture the sample complexity? And as you all know, the answer is yes, and that's for a very simple reason. What does the VC dimension say? If the VC dimension is 103, that means there's 100. That means there's 100 points which can be shattered. So that means that on those 100 points, the hypothesis class tells me nothing. My prior knowledge, my expert knowledge tells me nothing. Everything is possible in those 100 points. So now in those 100 points, if I just think of distributions that are concentrated in those 100 points, that are supported in those 100 points, then I don't have any prior knowledge. I'm back in this no free lunch situation, and I can't do anything better than memorizing on those 100 points. So in particular, if I have less than 50 points of data, I can't predict anything on the other 50. And so if I have like less than, say, VC dimension over 2 points, I cannot expect to get error better than a quarter or something like that. Okay? So that tells me that the VC dimension, not only does it actually bound the sample complexity, but it tightly captures the sample complexity. Something is learnable if and only if it has, a class is learnable if and only if it has finite VC dimension. And not only that, but the sample complexity is exactly captured by the VC dimension. It's bounded from above and from below by the VC dimension. Okay? And so this is a result of Vapnik, Chervonenkis in 1971. A few comments here, maybe we'll return to this later. So I wrote here the guarantees in the agnostic case. There's a little log 1 over epsilon that I don't know if you can see it. I don't know if you care, but it can be with the, oops. Okay, a bit more work, it can be removed. The other thing, the dependence on epsilon here, which I don't really care too much about in this talk, but here there's a 1 over epsilon squared dependence. If I limit just to the realizable case, I can improve this to 1 over epsilon dependence. And this just comes from the fact that the binomial tail bound is loose when you get close to 0. There's nothing fancy here. If you do want to get fancy, removing this log 1 over epsilon in this case is much harder. In fact, you cannot do it just with Theorem, but you can do it with, with other methods. And there's been a lot of effort to just removing this log 1 over epsilon. I'm going to skip all this, and eventually Steve Haneke managed to completely remove it, and we know log 1 over epsilons. But this is not so important for us. The more important thing for us is, what does this fundamental theorem of learning tell us? It really is fundamental. It tells us several things. Well, for one thing, it just tells us the answer. Okay, it tells us exactly what is learnable and exactly how many samples I need, with a big caveat: this is in the worst case over distributions, and we'll get back to that tomorrow. And I think that it also tells us something very profound, because think of what is this VC dimension. The VC dimension tells you on how many examples the prior knowledge tells you nothing. How many examples are completely, your prior knowledge is completely useless in them. Okay? So that means that if I have less than VC dimension examples, I can't falsify anything. I don't know anything. I just my prior knowledge is useless. And what the fundamental theorem of learning tells us, and this is a direct consequence of Sauer's lemma, is we have this very sharp transition. Once I can start falsifying, once the prior knowledge starts telling me something, it starts telling me everything. Once I can start falsifying, I can immediately transition to this regime when I can learn. I can very quickly learn everything. Okay, if I have just 100 times more points than the number of points I can falsify, I can already learn very well. And I think this is actually a pretty amazing fact. Okay, so I know you've all seen this before, but if you haven't thought about it this way, I do recommend just thinking about it a bit. The other thing it tells us, which is also very important, is it not only tells us when can we learn, but it tells us how, because it tells us that whenever we can learn with empirical discrimination. And remember that if we have high VC dimension, we just cannot learn. And if we have low VC dimension, we can learn with optimal sample complexity using empirical discrimination. So really, there's only one learning rule, or one template learning rule we have to care about, which is empirical discrimination. That's it. Okay? And this is also, I think quite impressive. Okay, but this is pesky issues of computation, which I'm going to completely ignore. But what I do want to talk about in the remaining, I have time. I have 40 minutes. Yeah, okay. What I want to talk about is, up until now, we only talked about flat inductive bias. And you might be thinking this is kind of our inductive bias is never flat, right? I mean, we never know. It's not like we have this, okay, this is plausible and this is not plausible. But rather, we always say, oh, some things are more plausible than others. What I'm going to try to, so we'll now yeah, Samori.
Just kind of comment
Sure.
that universal consistency is a different definition of learning.
Yes, that's true. Yeah.
In some sense, it's much better.
We can argue about that later. I'm going to get to that in a second. So this definition of learning is a very uniform definition. Actually, Samori, let's get to that in a bit. Okay. So I'm going to mention uniform consistency, and then I'm going to mention consistency, and then argue that the opposite of what you said. So we can maybe talk about it later. Okay. Where are we now? Okay, so what we're going to see is, first of all, we're going to treat a non-uniform bias, but then see that really we don't have to develop any machinery. So this machinery the machinery we have the machinery we developed so far, which is just based on this uniform convergence and bounding, capacity, bounding number of different behaviors, is going to give us everything we need for today and for tomorrow even. Okay, so right, so we want to get away from uniform bias. So instead of saying some things are plausible and some things are not plausible, instead we have some kind of think of it as a plausibility measure, right? So you can think of it as a prior, although I'm putting here quotes because I want to emphasize this is not a Bayesian prior. It is not that we're assuming the world behaves according to this prior, but rather this prior just encodes our bias of what things are more plausible than others. So like our expert Drian tells us, that some, a decision tree of size 3 is more plausible than a decision tree of size 50, or that, a decision list is more plausible than a decision tree, or something like that, okay? So you can think, and the reason you might be confused is that I am assuming for now that this prior is summable, and for convenience I'm normalizing it so it's summable to at most 1, and so to some of you it might look a bit like a probability distribution, but this is not a probability distribution, okay? So in said it can come from the expert knowledge telling us what is plausible or what is not, or maybe, for example, telling us if we're building a spam predictor that some words are more likely to be involved in spam prediction than others, or that, maybe telling us that lower frequencies are more important than higher frequencies, or something like that, okay? But maybe another way to think about it, yeah.
No, I mean, maybe not going to use conditional.
No, it's not the same as a Bayesian prior, because none of my analysis is based on the fact of anything actually drawn from this prior. So it's philosophically completely different. When we talk, maybe at the end, if I have time, I'll talk about PAC-Bayes, and then I'll directly, because that even looks even more Bayesian, and I'll argue why it's completely non-Bayesian. Okay, but maybe even a better way to think about it is that we prefer simpler things over more complicated things, right? We can prefer maybe a degree 2 polynomial over a degree 7 polynomial, a decision tree of size 20 over a decision tree of size 300, or a program with 50 lines of code over a program with 1,000 lines of code. So you can think of P as enclosed simplicity, right? Or maybe and this really goes back to this to Occam's principle that if you have multiple explanations, you should always prefer the simpler explanation. Okay, so the question is just what is simpler in this inductive. You can think of P as this how do we encode, how do we capture explanation? I should say this is attributed to Occam, but this predates Occam by several millennia. You can find the same principle at play in many other philosophers. Okay, so just to connect this a bit, maybe more explicitly to description length, and we're talking about P, but instead of talking about P, you can think of where does this P come from? Yeah.
If you have to choose between Occam and Maimonides,
yeah,
Occam's razor says pick Occam.
That's true, and which I think why this is attributed to Occam. In fact, it's a very good point. Okay, right, so we can think of this in particular, an important way of thinking of where does this P come from, and maybe this also goes, although I know that Misha would have a response to this also, but maybe a possible response to Misha. If we have, for example, some notion of description language, so for every hypothesis we have a way of describing it using a prefix ambiguous code, then Kraft's inequality tells us if we look at the negative log, 2 to the negative length of this of the description, this provides an appropriate prior from our prior measure. And again, this is, I'm not thinking of it as probability. This is just something that comes from Kraft's inequality. Okay, or maybe even more direct, rather than thinking of a mapping that maps each predictor to a descriptor, is think of the compiler, like something that maps a description to what it encodes. So this is like your programming language. So think of C here as the programming language C, right? Remember the C program to a function. Then now you can think of P as the to the essentially corresponding to the Kolmogorov complexity. How complicated is it to, how long does it take in my programming language to describe my function? And then this is my bias, is just to things that have a smaller description. Right, so, and then our learning rule there is just applying Occam's rule, in which I will call here the minimum description length rule. Is somebody going to argue with me about that name? No, nobody here. Okay, none of you are good. And I'll refer to this as a minimum description length learning rule. And it's against a template rule in the same way that ERM is a template rule that depends on a hypothesis class. It's a template rule that depends on my prior measure or description language or whatever. All these things are so. From my perspective, description language and prior are completely equivalent. They're just synonymous to each other, right? So again, maybe another answer to Misha. And I will be probably confusing between them as I talk. And it just chooses whatever explains the data, the predictor that has 0 error, and has the highest prior or shortest description language. Again, same thing. Okay, so and this is, I should say, appeared in a slightly more complicated and approximate form is Occam's rule. I think the first that introduced Occam into machine learning was Bloomer et al. In 1987, as far as I know. But the idea of using biasing to its short description goes all the way back to the initial work on inductive inference by Ray Solomonoff. And okay, so how can we analyze it? So the thing is that what we need now is, as I said, we're still just going to have a uniform convergence guarantee, except the uniform convergence guarantee is not going to be uniform anymore. Okay, so before we took this, we had this Hoeffding bound on each hypothesis separately, and we took a union bound over all of them, and for all of them we had the same failure probability delta. And all we're going to do now is we're going to have a different failure probability. We're going to allow a different failure probability to different hypotheses. So in a sense, think of it this way: we have a failure budget delta, and to a more likely hypothesis we more care about, we're going to give a higher budget of this delta, and to really crazy hypothesis, we're going to give a much smaller share of this delta. Okay. And now again, if we apply this, apply a union bound, I'm going to go through this very quickly. We get this non-uniform uniform convergence guarantee that bounds the difference in the expected empirical error, same as before, but instead of in terms of a uniform quantity, in terms of a quantity that depends on the predictor on which we're, maybe it's better to see it here, that depends on, the deviation depends on the predictor we're considering, right? So predictors would are more likely we're allowing higher, where predictors are less like, they're predictors are more complicated, which we have a smaller prior, we're giving them a higher, allowing them higher deviation. And now, again, this is a postal guarantee. What I care about is this. Did I not change it? I didn't change. Oh, okay, good. What I care about is applying it to the minimum description length rule. And what you can conclude from this is if I use the minimum description length rule, then I can, it outputs if there exists a predictor. What is this? Oh, sorry, this is not the slide intended to have here, but let's just jump straight to this. Okay, so if I use the minimum description length learning rule, I can learn, so if there exists if Julian has this predictor that's like perfect, okay, then I can learn a predictor that's almost perfect with but now my deviation depends on two ways to think of it. One, which is maybe the less useful way, is my excess error, my estimation error would depend on how complicated Julian's predictor is, maybe more directly to see it in terms of description length. Or another way to think about it is if I want to compete with Julian, I can compete with the number of samples that's linear in the length of Julian's description length. So I don't need to know in advance how long. It's not that I have to say that in my prior biases there exists a program with 100 lines of code. All I have to say that in my complexity measure is length of code. And Julian, what's your favorite programming language actually? Python. Okay. Okay. So so that's all I need to know, right? So I need my prior biases short Python programs. And it's just that the more complicated the predictor is, the more samples I need. But I can compete with any one of them. Okay, so in particular, what this tells me is, and goes back to what you said before, is I can learn actually all computable functions, right? All functions that have any that for which Julian can write a program. Again, just the sample complexity depends on this length of the problem. And okay, so let's ignore again the computational issues. But one thing you might think be asking is like, we're learning here a class. The class of all computable functions has infinite VC dimension. Okay, in fact, I can learn any countable class here, right? So this is. Why is there no contradiction to this fundamental theorem of learning, right? Because fundamental theorem of learning says we cannot learn things that have infinite VC dimension. Now I'm learning all computable functions. And the answer, of course, is that it all depends on this order of quantifiers, and goes back a bit to Samori's comment. Our definition of learning before was a uniform definition, and it required the sample complexity to not depend on the hypothesis, to have a uniform sample complexity. It depends on epsilon and delta, but not on the hypothesis. And the learning we're learning now is non-uniform learning, where the sample complexity does depend on the hypothesis. Okay, so. Okay, I don't have the slides. I thought I had them here. Maybe I have them. I probably have them. Oh, I know I have them later on. Okay, yeah. The orange. So the sample complexity m here is a function of not only epsilon delta, which that's fine. Just think of them as constant, but a function of what I'm competing with. Okay. Okay. So you can ask, okay, can we like characterize what we can learn in this case in this non-uniform way? So yeah, we can, but in order to do that, just hold your horses a tiny bit, because note that I have to do two things in order to tell you that. One is we talked about agnostic learning, and here our learning is not agnostic. Like where I'm only competing, the guarantee here is I'm only competing with the perfect predictors. If I'm trying to build a span predictor that's as good as Julian, I'm saying if Julian has a perfect span predictor, I can get a good one. But if Julian has a span predictor with 2% error, I'm not telling you anything. Okay? So let's first of all fix that problem. And that's easy to fix. So let's go back to this non-uniform convergence guarantee. And ERM just focuses on the first term, right? It takes this pH is uniform, so it doesn't care about the second term, and it only minimizes the first term, right? That's what ERM does, minimizes empirical error. And minimum description length insists of zero empirical error and only minimizes the second term. Okay? And what we can do instead is think of both terms together. Okay? And this is what Ian, following Vapnik, would call structural risk minimization. Okay? So the idea is, again, why structural risk? That we're really trying to we're doing bound minimization. We're developing not just we're not just minimizing the empirical risk. We're doing a bound on the quantity we care about and minimizing this entire bound. Okay, so this is a structural risk minimization learning rule, and if we plug this into our guarantees, we now get this agnostic guarantee. And again, now I can say that I can compete with anything Julian does. So if Julian has any predictor that's relatively short and has small error, then I can, with a number of samples that's proportional to how long it is, can get error, which is almost as good as Julian's. Okay. Okay. So one other comment I want to add here, if we're already talking about non-uniform uniform convergence, another thing we can be non-uniform about is the error of the predictor I'm competing with. So we saw before that we get this 1 over epsilon rate, which corresponds to like 1 over m excess error in the realizable case, and 1 over epsilon squared, which corresponds to 1 over squared of m in the non-realizable case. And we can adapt that to each predictor individually. So we can, by just taking union bound over Bernstein instead of Hoffning, we can get this optimistic grade guarantee. So we're bounding for each predictor the deviation in terms of this 1 over m term, and then a 1 over squared of m term, but it gets multiplied by the empirical error. So if the empirical error is 0, this term just goes away, and we have 1 over m. If this empirical error is high, then we do have this 1 over squared of m, and if the empirical error is low, then we have something in between. Okay. And again, you can plug in as guarantees and get learning guarantees with the same form. And maybe a better way to think about it is, what is the sample complexity? So the sample complexity in the realizable case. The realizable case, this is Julian's predictor H star. In the realizable case, Julian's predictor is perfect. This is 0, and this term goes away. It's just epsilon over epsilon. In the non-realizable case, when this is high, this is at most 1 over epsilon. Okay? So this interpolates between the 1 over epsilon and 1 over epsilon squared rate. And tomorrow we'll talk a bit more about why this distinction between 1 over epsilon and 1 over epsilon squared might be important in some cases. Okay? Okay, but what I do want to talk about now is the other thing we have to talk about in order to go to this general learnability, non-uniform learnability. So far, discussion of non-uniform learnability really did not go beyond cardinality. Like this minimum description length business, really all it doesn't look at the relationship between predictors. It just looks at how many predictors there are. In some sense, all I'm doing is I'm looking at hypothesis classes that correspond to like how many predictors are simpler than me, and I'm just counting them. Okay, but really I want to talk about none. So in particular, another way to see this, I need this P to be a discrete and summable. Okay, so how can I handle? But I want to be able to handle non-uniform over also continuous things. Like for example, the example I gave before of different polynomials. I want to say that degree 3 polynomials are simpler than degree 7 polynomials, but I cannot assign a discrete measure P that's going to be positive on all polynomials. Okay, so how can I do that? So there are 3 ways that I know to do this. Okay? One way to do this is to say that there's no such thing as continuous. Everything on the computer is discrete and just count bits. If you want to represent a polynomial, the coefficients are not real numbers, they're floating point numbers. You only have 64 bits. This actually provides very satisfying kind of a view of things, and then some would argue is maybe the more correct approach, but it's, at least from a mathematical perspective, is extremely unsatisfying. Another approach for dealing with the continuous is to explicitly allow continuous priors. I might, if I have time, talk about it at the end. So that's the PAC-Bayes you can view as a generalization and moves from discrete distributions to continuous. But the approach I mostly want to talk about is, instead of using a summable normal and hence normalized complexity measure, to use what we maybe more commonly use, which is just a completely non-summable abstract complexity measure. And this is what I refer to as the complexity measure approach. So in the complexity measure approach, which I would argue captures almost all of machine learning, is really, and we can argue about that tomorrow, is really the starting point is a complexity measure that just maps every predictor to its complexity. You can think of it as complexity or plausibility or whatever you want. The important thing is that the actual numeric value of this is completely not important. This does not have to be normalizable. In sense, all I'm doing is defining an order over the predictors. So all I care about is one predictor more complex than the other, right? So it's this kind of notion of which do I think is more complex than or more plausible than the other. Okay? And I can think of this inductive bias here. This captures inductive bias that there is a good and simple predictor. That's kind of and simple under this notion C. Okay, so how can we get learning guarantees from that, or I can get learning? And the idea is that if we think about what this complexity measure does, is really another way to think about it is defines a hierarchy of hypothesis classes, which are the sub-level sets of these of this complexity measure, right? So H3 here would be everything with complexity at most 3. Okay? H4 would be everything with complexity at most 4, and so forth. And within each one of these hypothesis classes, we can apply our learning guarantees from before. Yes, they're not learning. Our concentration guarantee, uniform concentration guarantee, would be before, with a deviation which depends on the VC dimension of this hypothesis class. And now the important thing here is that what I can do now is I can take a union bound over this entire hierarchy. Okay, so I can only, at least if I don't care about a factor of 2 in the big O here, right? Then I only care about I'm going to take only hypotheses that have VC dimension 1, 2, 4, 8, only the integer powers of 2. So I don't have many of these levels to worry about. And I can do the same trick of doing this non-uniform union bound over them. And get the following guarantee that I can say that for all hypotheses anywhere in this hierarchy, I get a deviation between empirical and expected that just depends on the VC dimension of this sublevel set. So that means now that for any the learning complexity for any for any hypothesis only depends again on just how many things are simpler than me, or not more complex than me, and not under the number, but now on the VC dimension, which we know is the right quantity. Okay, so again, using a bound minimization or structure risk minimization approach, we get this learning guarantee. Okay, so now maybe revising a bit what we said before, learning is not really about choosing a hypothesis class that's close to reality and not too big, because really we're never choosing a specific hypothesis class, but rather we're choosing a complexity measure. Okay, so we're really choosing you can think of it as a hierarchy of hypothesis classes or complexity measure. Both of these things are the same thing, right? Because I don't care about the actual value, just about the order. And so really all of machine learning boils down to choosing a complexity measure such that you can get close to reality without getting very big. Okay, that's it. Plus these pesky computational considerations, right? So the real challenge, I can easily do this by just choosing short programs. That would solve the problem, but now I want one of those hierarchies that I can also handle computationally. But we're not going to talk about computational considerations here. Okay, great. So where are we? So first of all, I just want to maybe answer Samori's question. We said that the fundamental theorem of learning tells me exactly what I can learn using a flat inductive bias, but it also really tells me exactly what I can learn also in this non-uniform way. So again, to do that, I have to define what I mean by non-uniform learning. And so in particular, if I change the definition to allow this non-uniformity that we had, I allow my sample complexity now depend on the hypothesis, and we have exactly the same way that we had in our guarantees, right? So now I'm asking, what classes can I learn with the sample complexity is allowed to depend on the hypothesis? Then a direct application of the fundamental theorem tells me, well, it's exactly things I can write as a hierarchy of VC classes, or in other words, anything that's a finite union of classes of finite VC dimension. Okay? And the important thing here, and this is that, and this is very important both to all the development today, even though I'm allowing my hypothesis, my sample complexity to depend on the hypothesis, what I'm not allowing to depend on is the source, the marginal distribution over X, the actual distribution. Okay, just on the it depends on like the answer, but not on the entire distribution. I could also even relax it further and say now I'm allowing the sample complexity to depend on the distribution. And there are definitely guarantees like that. For example, the standard nearest neighbor guarantees, definitely do depend. If you talk about the consistency of nearest neighbor, the sample complexity of nearest neighbor depends not just on how complicated the tessellation is, but also on the distribution. And I'm not going to tell. And then this becomes a bit trickier. And then you can ask Samori more about this, or Steve Haneke, and I forgot his name. This is very embarrassing. But there are other people that can tell you a lot about what is consistent. Samori, can you help me out here? No, Samori's not going to help me out. And this really goes beyond, but just to answer Samori, to me, this is a somewhat less interesting notion, and this is again very subjective, because I do care about the sample complexity. I do want to control the sample complexity, and I do want my sample complexity to actually be related to the complexity of the answer. But yeah, this is can talk about that later. Okay, so yeah.
I'm just only curious why. What is the thing you don't like about it?
Well, okay, there are two things I don't like about it. One is I don't know how to include it in this talk in a smooth way. And the other thing, I mean, so it's a very, in particular, if I look at it as a binary notion, okay, so let's separate the two things. So I think, honestly, that all these notions, if I just look at them as a binary notion, learnable or not learnable, they're not really useful. Okay? What I really care about is, I really want to talk about the sample complexity. So the fundamental theorem of learning, to me, what's important there is not the characterization of is it learnable or not, but the fact that it characterizes exactly a sample complexity. Okay. So also here, if you maybe could tell me something a bit more, the thing is now, if I tell you the sample complexity corresponds to the complexity of the answer, to the description of the answer, that's something I can, I can think of, I can understand. If you tell me the sample complexity can be arbitrarily large in a way that I'm not really like, finite for any distribution, it's finite, but it can really explode with the distribution. To me, this is maybe not saying much. Okay, maybe that's like my best answer here.
Just one comment. I mean, that is true also about
this definition. I agree. I completely agree. So as I said, all these definitions as written here are binary, and hence all of them suffer from this problem from my perspective. But the thing is that I can actually get the positive results. I can actually, even though I'm writing the definition this way, I can actually get tight characterization of the sample complexity for these notions in a way that actually captures the sample complexity. And the results that I'm aware of for this consistency notion are generally are these like non-quantitative in nature. But that's, I mean, this is maybe maybe somebody listening online can correct me on this. Yes, Daniel.
Metric entropy fit in for this one, for the last one.
So metric entropy. So metric entropy is distribution specific, but yeah. So you can ask about, but that's a bit different. That's if you restrict the. I don't think it exactly. So metric entropy gives you a result that things are not learnable in general, but learnable under a specific distribution. That's distribution-specific learning. The notion as written here and as studied by Steve and his co-authors is really you're still wanting to be learnable for any distribution. It's just the sample complexity depends on the distribution. There has to be finite for any distribution. But let's move on, because Matusz is going to kick me out here soon, and I do want to talk about two important things and one non-important thing. So okay, so what I do want to talk about, rather than this consistency notion, is about structural risk minimization in practice. And structural risk minimization is really super practical and is the way we actually learn. Now, you might be looking at this and thinking, what am I talking about? Like, nobody minimizes a bound, right? Nobody minimizes growth. Plus, it doesn't make any sense to do this. This bound is, for several reasons. First of all, this suggests that in order to learn, I have to calculate the VC dimension of the sublevel sets, and I don't generally know how to do that. If that was really necessary, they really would have a lot of employment for theory people in learning companies. And this is not actually necessary. The second is I'm minimizing a bound here that's super loose. I know, it's actually, I can get the learning guarantee with any constant here, but really to get something tight, I have to get the correct constant, and not just constant. We just said that these guarantees are like, relying here on Hafting bound, which is super loose and you should never do anyway. Nevertheless, I would argue that this is exactly the rule that is actually used. The thing is, the way it's used is a bit different. So what we actually do is this objective is monotone in the empirical error and the complexity C, because VC dimension is monotone in the inclusion, and so monotone in the level in which I cut the set. And so what we actually do is we just think of it as a bicriterial optimization problem. We just try to minimize both of these. We minimize the empirical error and the complexity. Okay? So what's a bicriterial optimization problem? And this is, I think, the most important slide in the entire talk today, because this is how learning actually looks like. So we have two objectives. We have the empirical error and we have the complexity. We want to find a predictor that has small empirical error, right, that fits the data and is simple, right, and is over here. So we want to find a predictor that's over here. There's no such predictor, right? Okay, so we want to minimize both, and this is the attainable set, all this yellow stuff. So actually, I should maybe draw it like this, but any predictor here, any combination here is possible. There's some predictor with small complexity, but empirical error over here, and there's also one with lower empirical error but higher complexity here. Which one should I choose? Well, I don't know, but I definitely should choose one that's on the frontier, right? That's on this Pareto frontier, that's Pareto optimal, in which I can't improve one of them without hurting the other, right? It doesn't make any sense for me to use this predictor because I can find a better predictor that's both simpler and better fits the data. Okay? So I want to restrict myself in the Pareto frontier. Another way to think of the Pareto frontier is just the regularization path, right? So I can, roughly speaking, get all the points in the Pareto frontier by, for example, minimizing some combination of the empirical error plus a regularization parameter times the complexity measure. Okay? And as I vary lambda, I explore the frontier. Right? So lambda, when lambda goes to 0, I'm going to select this point. Okay? And when lambda goes to infinity, I'm going to, do I have that there? Yeah. And when lambda goes to infinity, I'm going to select this point. Okay? So what is this point? Just to also map ourselves to what's going on here. Let's compare this to empirical risk minimization. Empirical risk minimization just cares about the empirical error. Okay? And so all of these points are empirical risk minimizers. Okay? So all of these points have minimal empirical error, okay? But different complexities. When lambda goes to 0, the point I'm going to choose is this point. We have a special name for this point. What is this point here? What does this predictor correspond to? Which learning rule returns this predictor that's over here? Minimum description length, right? So this is a minimum description length predictor. It's the endpoint of all the ERMs. The ERM predictor with the smallest, that's simplest, the smallest complexity. Okay, and now we're saying, okay, let's not insist on this. Let's look somewhere along here. Okay. Okay, so this gives us this entire frontier. So what do I mean by a learning rule that returns a point in the frontier? And also, this is not what we wanted here. Here we wanted a specific combination. The thing is that we're just minimizing some monotone function of the empirical error and the complexity, and hence this predictor is somewhere along this frontier. I don't know where, but that's fine. I now reduce my problem to just a single parameter problem, and I can choose the point of the frontier using validation. Okay? Or another, if you prefer thinking about it this way, I'm choosing lambda using validation. And this is exactly what we do. Okay? And so structural risk minimization is exactly the learning rule that we actually use all the time. Okay, and we either do this explicitly by actually solving a regularized problem and searching over this lambda with some complexity measure, or we do this implicitly. Okay, so the way we usually think about it doing implicitly, I'm sure all of you have heard, and actually Matusz mentioned this morning, implicit regularization, the norm, and with a norm, but we didn't talk about norms yet. We'll only talk about it tomorrow, but we don't have to talk about norms. We can talk about the most simplest optimization algorithm in learning that I can think of, or the most I can think of, but like, when at least the first learning method that I teach when I teach machine learning is decision trees, learning decision trees, okay? So how do you learn with decision trees? Well, you can say, well, I want to find a consistent decision trees, right? So this is realizable learning. I just want to find a consistent decision tree. So this is kind of like doing ERM in a realizable case. Okay, how do I find a consistent decision tree? Well, I have this greedy iterative algorithm. I start with a tree, and then I have I even have the animation here. I start with an empty tree, and then each time I split one of the leaves. This is, I think, for spam prediction until I get to a 0 error. Okay, so doing that, this is a learning rule for implementing ERM over decision trees. Okay, but what's important with this learning rule is that if I run it all the way to the end, then I just do ERM. I minimize over all decision trees. But what happens if I stop early? Okay, which is actually what we frequently do in practice, both with building decision trees or with running gradient descent. Okay, so if I stop early, in this case, I'm going to have a decision tree of bounded size. So really what's going on here is as I track the progression of the algorithm, I'm optimizing, not exactly, right, because this is a hard computational problem, but I'm approximately optimizing over sublevel sets of, I'm going to ignore that for a second, over sublevel sets of, I'm almost done, over a complexity measure, which is size of decision tree. Okay? And even if I optimize all the way to the end, even if I don't do early stopping, the decision tree that I'm going to end up with is not just any decision tree that has 0 error, but it's going to be a relatively small decision tree that has 0 error. So in a sense, you can think about the optimization here is implicitly, in this case, approximately, also exploring the same Pareto optimal frontier. Okay, and this is something we'll get back to tomorrow, and also another teaser, maybe especially for Misha. Note that even when talking about just decision trees, it's super easy to see a phenomena that we now see all the time. Which note that even in a non-realizable case here, okay, so the right thing to do here is to early stop, right? To choose a point like somewhere here in the frontier. But if I don't do that and I optimize, I do overfit a bit, but this doesn't jump up to infinity, right? What we see here, okay, is that even in this case, doing this using this minimum description length principle leads to some kind of maybe tempered overfitting. And again, this is, we'll talk about this a bit more tomorrow, and I'm sure other people also talk about this, but just want to point it out here. Okay, I'm not going to talk about PAC-Bayes. Sorry, somebody asked us, sorry, Misha, but I think I need to end here. Thanks.
Just a quick warning / announcement about the schedule. So I'll try to start the next talk on time. So please be quick with the break, because then we have reception at 4 p.m. and the assignment staff want us out at 5.
You can ask questions tomorrow.